So this is the second part of solution series. So today I am going to explain the rest organic question which are asked in JAM 2022 paper. So the first question is, it is a named reaction known as Carney-Jarrell reaction. So in every named reaction, what do you have to remember? You have to remember substrate, reagent and product. So for Carney-Jarrell reaction, the substrate is like that, having no alpha hydrogen, carbonyl compound having no alpha hydrogen, and reagent is your concentrated base like sodium hydroxide, and your product is sodium carboxylate and alcohol. So in Carney-Jarrell reaction we get two products, one is sodium carboxylate and one is alcohol. For that we need two equivalent of substrate. So the substrate contains two functional group, two carbonyl group, that is aldehyde having no alpha hydrogen, and the reagent is sodium hydroxide. So these two combinations shows this is Carney-Jarrell reaction. So what is the product we will get in that reaction? So we will get two products, one is sodium carboxylate and one is alcohol. So one functional group will change to sodium carboxylate and one will change to alcohol. So what is the general mechanism of Carney-Jarrell reaction? The mechanism is like that. Sodium hydroxide is act as sodium plus and OH minus, and OH minus is a base as well as a good nucleophile. If there is no alpha hydrogen, there is no possibility of acting as a base, so it will act as a nucleophile. So it will attack one of the carbonyl carbon of the aldehyde, then the double bond will migrate to oxygen, then we will get O minus, here your hydrogen and hydroxide and aldehyde here. Now when the electron comes back to form the double bond, there is an hydride shift from the carbonyl to the another carbonyl carbon. Then there is, and that double bond will shift towards oxygen. So negative charge over oxygen, one hydrogen already is there and one comes from that shift, and here it is carboxylic acid. So after that, that O minus will extract that proton of the carboxylic acid group and it forms a carboxylate. So here is your benzene. Now it is a carboxylate and here it is your alcohol, and carboxylate contain the counter ion as sodium, that is called sodium carboxylate and alcohol. So this will be the product of that reaction. So for Carney-Jarrell reaction you have to know the mechanism as well as the substrate and the condition. So next go to the next question. So the next question is like that. So one fixture, this is called your fixture projection, right? Fixture projection. So the condition given, the reagent given is sodium cyanide, acetone and heat. So it is a polar aprotic solvent. So in polar aprotic solvent there is possibility of formation of, there is possibility of SN2 type of reaction. And here in sodium cyanide, the cyanide ion is act as a nucleophile. and the group and that substrate contain a OTS as a good living group. So it's showing like a SN2 type of reaction is going to happen. So we need to find out the stereochemistry of the product. So every time remember Fischer projection is eclipsed conversion. Eclipsed form. So if you try to convert into in any conformer, you have to write down the eclipsed eclipsed conformer. So how to write if I want to convert Fischer to Newman, then to Sohors. So how I will convert? See, in Fischer carbon, this one, let's consider this one as a front carbon and this one as a back carbon. So how to represent the Fischer configuration or conformers? Sorry, conformers. So you have to represent the front carbon like a dot and back carbon like a circle. So the front carbon contain methyl down. So methyl down, hydrogen on the left, and OTS on the right. So what I said, the Fischer conformers is the eclipse conformers. So when we are converting into Fischer to Newman, you have to write it in the eclipsed form. So the rare carbon containing pH. So I have to represent in Fischer conversion to Newman 1 and with eclipse conformers. So pH I have to put at the methyl side of the methyl and hydrogen on the right side and methyl on the left side. So this is the eclipse conformers and there will be a steric repulsion. So we have to convert into staggered one. How we will convert? We will rotate the carbon, the back carbon like pH here and hydrogen here. Methyl will be on that side. Anticlockwise rotation. So the front carbon will remain same like this. Hydrogen, OTS and methyl, and the rear carbon is pH will come to here, hydrogen here and methyl here. Now if I want to convert into staggered conform sorry into that Sohor's conformation, how I will convert? So Sohor's conformation is like the front carbon OTS Me, then there will be a line and here is your pH, that methyl on the left side and methyl on the right side. So if I again want to convert the Sohor's projection to your uh, flying Weierstrass conformer, how I will convert? Let see, this is the main axis, so I have to write the main axis like this. OTS on the above the plane, like it is present on the right side, right? So the right side one is the above the plane and the left side one is the down the plane, and here hydrogen present on the left side. So left side is means it is down the plane and right side means it is above the plane. Now you add your reagent sodium cyanide and acetone as a solvent and heat. Then the sodium cyanide will act as a nucleophile. It will attack to the carbon, a SN2 type of reaction, and OTS will leave. Then what we will get? We will get cyanide as a incoming nucleophile and it replaces the OTS and it will come from the below the plane and the stereochemistry will be this. So in SN2 reaction the stereochemistry get input, that all you know, right? So as the OTS is above the plane, so the incoming nucleophile will attack from the down the plane That's why I represent this on the dash line. So this will be your product in the given question. So what will happen in SN2 reaction? Stereochemistry get inverted. And what is the conditions? Polar aprotic solvent. Like your acetone or your DMSO. Whatever you mean by DMSO? Dimethyl sulfoxide. DMF. What DMF? Dimethyl formamide. This is the chemical structure of dimethyl formamide. So this will be your product in the given question. Understood this question? So next move to the next question. So in the next question, what given? So a IUPAC nomenclature is given and a condition like sodium ethoxide and ethanol is there. So you have to predict which one is their product. So for that you have to first able to convert this IUPAC name into your structural form. Okay. So what it is represent 2S3R 2-chloro 3-phenyl butane. So the parent name is butane. So for butane we need your 4 carbon and it's showing at 2 position it contain a chlorine. Let this one 1, 2, 3, 4 and chlorine at 2 position and 3 is phenyl. Now we have to assign like the stereochemistry at 2 and 3. S and R, how we will represent? So for that we need to mention this carbon as a chiral one. So for S, so let's try which one will be your. So first fix the carbon center 2. So for S, if I represent chlorine as above the plane and hydrogen is below the plane. Now what is the stereochemistry? So we have to give the priority. Chlorine is 1, this carbon is 2, this is a 3 and the rotation is clockwise rotation. That means the stereochemistry is R and the hydrogen is below the plane, so no need to change. So this will be not our exact stereochemistry. So what will be the our stereochemistry if I put the chlorine is down and hydrogen at up? So now assign chlorine is 1, carbon 2, this carbon 3. It is a clockwise rotation. That means R, but the fourth priority group at the above the plane. So the configuration will change to S. So 2S, we will get 2S. So now see the stereochemistry at carbon 3. So assign here it is chlorine. Let it be like this. Now just put pH at above the plane and hydrogen is down the plane. So the priority is like, see the carbon, it also contain a carbon, it also contain carbon, it also contain carbon and it contain chlorine, so that will be your highest priority. Then 1, then pH becomes your 2, this carbon is 3 and hydrogen is the down the plane. The the movement is 1 to 3, that is anti-clockwise, that means it is S and hydrogen is down the plane, so no need to change, but we need R configuration at carbon 3. So what we have to do? We have to put pH as down the plane, hydrogen as above the plane and here chlorine. Now assign this one 1, pH is your 2, this carbon is 3. The rotation is anti-clockwise S, but this time the hydrogen is above the plane. So the configuration will change to R. So what we will get at the final? We will get your chlorine as, sorry, chlorine, this one, chlorine down the plane and pH also down the plane, and hydrogen is above the plane here, here also above the plane. So this is the structural form of the given IUPAC name. So then you have to add what? Sodium ethoxide and ethanol. So these two conditions will favor your E2 type of elimination. So for E2 type of elimination, we need a anti-periplanar rearrangement side, sorry, anti-periplanar arrangement, like both the obstructing hydrogen and leaving group should be anti to each other, right? So now we have to convert the given your Wegner's conformation to Sohor's conformation. So how we will convert this to a Sohor's conformation? So let me do here. So what we get? Let me write this. Okay. So what we get? We get Cl is your down the plane and pH also down the plane. Hydrogen is above the plane. Here also hydrogen is above the plane. So if I want to convert this into Sohor's projection, how I will write? See, I write like this. So this is methyl, this is methyl. So chlorine is down the plane. That means I have to represent on the left side, and hydrogen is above the plane. That means I have to represent on the right side. Here pH at the downside. That means I have to represent on left and hydrogen right. So now rotate that carbon, the front carbon or the this carbon number 2, 60° anticlockwise, and this carbon number 3, 60° clockwise. Then we will get chlorine here and hydrogen will go to here. Then both the hydrogen and chlorine will be at the anti position. See what we will get? We will get hydrogen here. If this hydrogen will go to this methyl position, and methyl will come to pH position, that is phenyl, and phenyl will go to your hydrogen position. So in front carbon, if I rotate like the same way, so the chlorine will occupy the methyl position and methyl will occupy hydrogen position, and hydrogen will occupy your chlorine position. Now both the leaving group and the obstructing hydrogen is anti to each other. Now your base, that is OET minus, that is ethoxide minus, will obstruct this hydrogen, and the sigma bond electron will come to the your sigma star orbital of carbon chlorine, and chlorine will leaves. That is the reason why we need anti-periplanar rearrangement. Then we will get a minus HCl, and we will get, sorry, not minus HCl, we will get ethanol and Cl minus. We will get ethanol and Cl minus, and here it is forming a double bond. Double bond contain hydrogen on the left side, methyl on the right side. Here methyl on the left side and phenyl on the right side. Now the configuration is both the priority, like if I assign the priority across the double bond, like here it contain carbon, here it contain hydrogen, here it contain both the carbon pH 1, so methyl will get 2. So the configuration is Z isomers. So at the end of the elimination we will get Z isomer. That we have to answer, like which isomer we will get. So this is the way to solve this type of question. So hopefully you get understand. So now the next question is the number of signal in 1H NMR. So so in NMR we have to know like all the equivalent hydrogen will show the same peak. Like we have to find out the environment of the each hydrogen. If two hydrogen are in same environment, then the two hydrogen will show one peak. See, if you are given a structure like this, like a cyclic structure, you have to find out the number of mirror plane. So there is a symmetry, right? Like we can pass a plane about that middle of that compound. Then this carbon, if it is A, then this carbon also A. If it is B, this carbon also B. And it is C, it is also, sorry, it is D. Okay, so when you are passing the plane, we have to, after passing we have to consider the only one half of the molecule. So the one half of the molecule is seems like this, right? Like this. So now there is a possibility of passing a plane over here. If we pass the plane here, then that A will reflect here A, and now D and C becomes equal. Like that will reflect C, and this also, this hydrogen will reflect here. So what we get after passing the second plane, we will get a methyl here, one hydrogen here, one hydrogen here. So these three will show three different peak in 1H NMR. So what we get if we represent the complete structure? So what we get at the end? So here the three hydrogen is similar on the right side, and this carbon also similar. So we will get 12 hydrogen of same type. Here it is 3, here 3, here 3, here 3. So 12 hydrogen will show one peak in 1H NMR. Now this, if this hydrogen is B, this hydrogen also B, this hydrogen also B, this hydrogen also B. So 4 hydrogen will show one peak, and here if it is C, and these three also C, then 6 hydrogen will show one peak. So in 1H NMR we will get 3 peak. So that is the number of signal we will get in 1H NMR. See, you can confirm by another way, by considering their environment. See, if I am considering this hydrogen, okay, let me change the color. See, now I am considering 3 hydrogen at, like I am representing the 3 hydrogen at C. See, these all 3 hydrogens contain both the side hydrogen. Here also the 3 hydrogen contain both the side hydrogen, and both hydrogen are also similar. That means both the C hydrogen on the different carbons are similar type. same environment, and they will show only one peak. So this is the way you have to find out if any ring system or any, like if any compound like this is given. So you have to find out the number of 1H signal. Okay, so what do you have to do? You have to pass a mirror. Let pass a mirror, this carbon. It will cut like this, right? Now this half we will eliminate this half. Now there is also a possibility to cut that ring like this. Then these hydrogen and these hydrogens are similar. So here also, so both the four hydrogen will show one peak, and that aldehydic proton will show one peak. So there will be two peak in 1H NMR. Okay, so this is the way you have to solve. So the next question. So the next question is conversion of benzaldehyde to acetophenone. So it is a multiple answer type question. So like out of four, any one or any two or all of four maybe your answer. So you have to find out. So let's solve each of the option. The first option given is your CH3COCl and AlCl3. That is called acetyl chloride and it is aluminum trichloride. So these two combination we will find at Friedel-Crafts acylation reaction. So in Friedel-Crafts acylation reaction, we will get a electrophile like this, and it will get attached to, if it is a your electron donating group, then the electrophile will come at ortho and para position. If it is a electron withdrawing group, it will come at meta position. So like at the end, this group will add to the benzene ring. Like any group here, it will either attach to this ortho position or para position or your meta position. But here the change is like only hydrogen get replaced by methyl. There is no change in the phenyl, that is benzene ring. So this option 1 is eliminated. So we can't transfer the substrate into product by using the option 1. So that is eliminated. Now move to the next option. So what is the next option? So it is called as dithiol, the first reagent dithiol and BF3. BF3 is a Lewis acid. So these two combinations are used to protect carbonyl group. Carbonyl group protection. Okay. So if we will protect the carbonyl group of substrate by the reagent, like one I reagent, we will get this as a product. After that there is butyl lithium and methyl iodide. So butyl lithium is a base, so it will abstract the more acidic proton. So this proton is the more acidic proton because after abstraction of this proton, the negative charge will form here, that will get stabilized by the empty d orbital of the sulfur. So after adding that base, we will get, a negative charge here. Now we have methyl iodide. So there will be a SN2 type of reaction. We will get methyl at the position of hydrogen with protected carbonyl group. Now in the last step they added HgCl2, that is used to deprotect that protecting group we will get your carbonyl back. So this is the product. So the option B is one of the correct option. Now we have to check more two option, like anyone is satisfying our reaction. So there is a note, if I add sodium amalgam here, so what will be your product? So if you know the answer, just write your answer in comment. Then I am going to explain what will be your product if you add sodium amalgam in that protected carbonyl in the next video. Okay, try to find out what we will get. Okay, now move to the C option. So C option, it contains sodium amide NaNH2 and your methyl iodide. So it can exist as sodium plus and NH2 minus. So NH2 minus can act as a base as well as nucleophile. So if it acts as a nucleophile and it will add to the carbonyl group, we will get O minus hydrogen and NH2, and that O minus can attack to the methyl and iodine get lost. We will get a product like this. So this also not our required product. So option C also cancelled. Now check what we will get in option D. So what is in option D? Option D is your first is Grignard reagent. So Grignard reagent will add to that carbonyl group. We will get pH your O minus MgBr plus with a methyl group at carbonyl carbon and hydrogen. After that, like acidic medium, so it will form your alcohol, get neutralized and it will form a alcohol. After that, there is PCC. PCC is a oxidizing agent. It will oxidize alcohol to your carbonyl group, like secondary alcohol to carbonyl group and primary, okay, secondary OH to ketone, 1 degree OH to your acid. Not acid, it basically converted to your aldehyde. If then you have any proton source or like acidic medium, then the aldehyde will convert it to your carboxylic acid group. So we will get this as a product, and that is the product given in the question. So the option D also the correct option. So the answer of that question is your option B and D. Now the next question. The question is we have to find out of all the structure which one is aromatic one. So the next question is we have to find out of all the structure how many are aromatic compound. So for aromatic compound, what is the criteria? Criteria is it should be planar, it obey Huckel rule, that is 4n plus 2 equal to number of pi electron, and n should be your integers. All the carbons should be or all the atoms should be sp2 hybridized, and the structure should be cyclic one. So these are the main criteria for a compound to be a aromatic one. So next let's move to each of the structure. So this is the first structure, that is called as cyclooctatetraene C or T, cyclooctatetraene. tetraene. So what happened, like it seems like a aromatic compound, but it is non-planar. The actual structure of the cyclooctatetraene is like this. So this is the actual structure of the cyclooctatetraene, and that structure is non-planar. So that is not a aromatic compound. Here it is a cyclopentadiene. It contains here a sp2 carbon, sp2 carbon, sp2 carbon, sp2 carbon, but the carbon is sp3. So for compound to be aromatic one, all the carbons would be sp2. So this also not our aromatic one. Now this carbon sp2, this carbon sp2, this also, all the carbon are sp2. Now we have to find out it is a planar compound. Yes, it is a planar compound. Now we have to find out like it is satisfying Huckel rule or not. So the structure we can represent like this also. Here your double bond, double bond, double bond, O minus, and here it is your positive charge. Now the number of pi electron is 2 for this double bond, 2 for this, 2 for this, like 6. Then 4n plus 2 equal to 6, n is equal to 1. It is integer. So that compound is your aromatic. So this is aromatic. Now here all the carbons are sp2, as well as all the pi bonds are in conjugations, but it is a non-planar compound because the hydrogen at the carbon shows some steric repulsion. For that it is not a aromatic compound. It is non-aromatic. So in that example, this carbon is sp2, this carbon is sp2, the nitrogen here also sp2, it also sp2, the nitrogen also sp2, and it is a planar compound. The number of pi electron is 2, 4, and 1 lone pair of the nitrogen take part in the aromaticity. So the number of pi electron is 6, n is equal to yours 1. So this also your aromatic one. Now this is called as your furan, and this ring is known as imidazole ring. So furan is aromatic one, everyone knows, like one of the lone pair of the oxygen take part in the conjugation. So number of pi electron is 6, n equal to yours 1. So this also aromatic. This is called as your, it is a acyclic system. So although all the double bond are in conjugated position, but as it is a acyclic system, so we can't consider it is an aromatic one. So this is not aromatic one. So here it is known as cyclobutadiene. Cyclobutadiene. So it contains 4 pi electrons. So 4n plus 2 is equal to your 4, n is equal to your half, that is 0.5. So it is not an integer. So it is anti-aromatic compound, not aromatic one. So this also not a aromatic compound. Here it is a cyclopropane anion. It contains 2 pi electron from this double bond and 2 electron from the negative charge. So the number of pi electron is 4. 4n plus 2 equal to 4. Your n equal to 2 minus 4. That is your half. So it is half means 0.5. So it is not a aromatic compound. Here all the carbons and the oxygen is sp2. It is a planar compound, and number of pi electron is 2, 4, 6. So it is a aromatic compound. Here the number of pi electron is 6 and all are sp2 hybridized, so it also a aromatic compound. Here this carbon is sp3, this carbon also sp3, this carbon also sp3. So not all the carbon are sp2, so this is not also a aromatic compound. So the number of aromatic compound is 1, 2, 3, 4. So there is 4 aromatic compound. Okay, the next question is alanine is given HBr, we have to add HBr and we have to predict the major product and the number of isomers forming the major product. So if we add HBr to that alanine, we will get a product like hydrogen here and CH2 here. This is one and your CH2PH, CH2Br on that side, hydrogen on the product. So these two stereoisomers we will get. So here it is 1, 2, here it is 1, 2. So we will get E isomers. Here it is pH1, hydrogen 2, 1, 2. We will get E isomers. So the number of stereoisomers is 2 and these are the product. So this is the answer of that question. So this is the last question in the organic part. I am going to explain. This is based on the NMR spectroscopy, and that question is generally known as structure elucidation from your NMR plus IR and mass data. So here mass data is not given, only your 1H NMR and your IR value is given. So in every case IR value may vary, it's depend upon the substituent. So you have to consider IR value at the end. If you are not able to identify on the basis of 1H NMR or 13C NMR, then you have to go to IR1. Otherwise, you have to look on to the 1H NMR only. So for that, I need to say something. The range for aromatic range. The peak will come at 6.5 to 8.5 ppm, and aldehyde 8.5 to your 10.5, acid 10.5 ppm to 12.5 ppm, and if it is represented as 3.5 to 4 ppm and singlet, then the group is OCH3 or OMe, and if it is 4 to 4.5 ppm, then it is OCH2O. Okay, so these are the point you have to remember. Now try to eliminate each of the option. So here in aromatic region, like 6.5 to 8.5, so it will come as 6.7 and 7.1. Both will come in aromatic region. So aromatic region, there is 2 and 2, like 4 hydrogen is there. So we have to find out which of the option contain 4 aromatic hydrogen. So here it also contain 4 aromatic hydrogen in option A. B also, here 1 hydrogen, 1 hydrogen, 1 hydrogen, and 4 hydrogen. And C 4 hydrogen, and D also 4 hydrogen. Now it's showing like 2 hydrogen have their environment same, and these 2 hydrogen also have their environment same. So for that, what we have to do, we have to look at to the like the plane. See, these hydrogen contain methyl on the left side and right side a hydrogen. This hydrogen also contain methyl on the left side and right side hydrogen. So this hydrogen, if I represent this hydrogen as A, this then this also be A, and this one B, this one also B, because it contain left side hydrogen, right side ON. So these two hydrogen are same, these two hydrogen are same. Here also HA, HA, HB and HB. Here also here HA, HA, HB, HB. Now in that, if I am representing this hydrogen as A, this will be your HB, this will be your HB, this will be your HD, because it contains left side hydrogen, right side aldehyde. This hydrogen contains right side hydrogen, left side your methoxy group. This contain left side methoxy, right side aldehyde group. So both the hydrogen is 4. Sorry, both the hydrogen are different. That means 4 hydrogen will show different peak, but it will come in aromatic region. So but here it's showing two hydrogens showing same peak, another two hydrogens showing same peak. So option D we can eliminate. Now, like 3 hydrogen singlet range is 3.8. So we have to look at like any of our option contain OMe group or not. See, the option 1 contain OMe group, option B also contain OMe group, option C also contain OMe group. So on the basis of this value we can differentiate out of 3. So now the next one, like 2 hydrogen doublet. When 2 hydrogen will show doublet, when it contain neighboring carbon contain 1 hydrogen, right? How we will calculate the splitting? Like 2n I plus 1. This is the formula by which we can calculate the splitting. So 2n is your number of equivalent proton. Let n be n, and I is the it is called as nuclear magnetic spin. Like for hydrogen it is half and 1, so 2 cancel and it is doublet, that means 2. Now n plus 1 is equal to 2, n is equal to 1, that means so 1 hydrogen should be there next to that carbon, then these 2 hydrogen will show doublet. So let's find out any carbon containing 2 hydrogen and next carbon contain 1 hydrogen. So here there is no such carbon containing 1 hydrogen. So 2 hydrogen we have to find out. See, here it is 2 hydrogen. But the next carbon, there is no next carbon. One is oxygen. So this is not the correct option. So B is also eliminated. Now C. C contain 2 hydrogen. And the next carbon contain 1 hydrogen. So these 2 hydrogen can show doublet due to here this aldehyde proton. Okay, and at the end, so option A also eliminated because there is no carbon containing 2 hydrogen. So option A also eliminated. Now what it is represent, 1 hydrogen triplet. If these hydrogens showing doublet because of this hydrogen, these will be so triplet because of these 2 hydrogen, because if these 2 hydrogen are coupled with that hydrogen, then that hydrogen also will couple with that 2 hydrogen. So aldehyde will come at 8.5 to 10.5. It will coming at 9.72 ppm, and your 1 hydrogen showing triplet. So this will be your product. So by the help of NMR only we find out which one is our correct option. But see, IR also, like aldehyde will come at 720 centimeter inverse. So the correct option is C is your answer, right?